Okay, so this is the fourth lecture in chapter 5, which will be discussing the mass balance. I am still discussing 5-2, which is conservation of mass. And this is the second lecture talking about examples or problems in mass balance. Now, the problem that I'm about to discuss is in front of you. I'm going to read it and explain it on this figure. So water is pumped into a 10-foot diameter tank. Water is pumped into a 10-foot diameter tank at a rate of 10 feet cube per minute. So the diameter of this tank, as is shown here, is 10 feet. And the rate at which the water is added is 10 feet cube per minute. So this is, you can say this is as what? As, sorry for this. So V dot N. This is V dot N, which is 10 feet cube per minute. If the tank, okay, now if the tank were initially empty, so the tank was empty, there was no water in the tank initially, and if water were to leave the tank at a rate dependent on the liquid level according to the relationship Q out is equal to H. So this is the relation which is given to us as what? As V out. Okay, is equal to this. So V out is equal to Q. V out is equal to Q. It's just different notation. Okay, just different name, but the meaning is the same. Where the units of the constant 2 are feet square per minute and h are feet. He is just telling you that the unit of this thing here, the unit of this is consistent. I mean, when you multiply foot square per minute times foot, you will get feet cube per minute, which is the same as this one, volumetric flow rate. Now, what is required? He's asking for find the height of the liquid in the tank as a function of time. So he's looking for h as a function of time. In the previous example, it was v as a function of time, volume as a function of time. Now he's asking for height as a function of time. Okay, this is what is required. So how to tackle this problem? First of all, I want to show you this integral relation, which will be used heavily, maybe in 3 more examples or 2 more examples. That is the integral of dx ax plus b is equal 1 over a ln ax plus b. We'll use it in the coming examples. So this is the equation that I have showed you, the integral relation. I'm going to keep it here. So when I need it, I will refer to it. And as usual, you start by thinking about the assumptions. So what are the assumptions? The first assumption is water is incompressible. The second assumption is for the conservation of mass. As usual, you will say that there is no chemical reaction, so consumption equal to generation equal to 0. And so I can write the general conservation of mass equation, which is dmCv by dt is equal to mn minus m out. Okay, and now we have to think about the link between the mass flow rate, and the head or the height. Because in the previous problem it was the link between volume and time. Now it is height and time. But here I have mass. So first of all, I will do the same thing that I have done in the previous example. I want to get rid of the mass in terms of volume. So I can do the same thing that I have done again. Let me just write it in black. So D instead of M, so rho VCV divided by dt equals rho Vn minus rho V out. And since we said we have the incompressible flow, so I can take this density outside the differential, and then I can just cancel them. Okay, I can cancel them. So I have the equation, which is this: dV by dt equals Vn minus V out. And dV, this is طبعا the volume, the controlled volume, which is dV CV dt. And now this will lead me to the following: dV by dt is equal to, what is Vn? I have it here, which is 10 feet cubed per minute, minus this one. We said Q is equal to V out, which is 2h. So on one side I have V, on the other side I have H. So it seems I want to get rid of this V in terms of H. So what is the link between volume and height? The link is the following. This is the link. Let me just write it in blue here. So you know that V of a cylinder, this is a cylinder tank. So V is equal to A, which is the area of, let us say, of the circle with the base, times the height. Okay, this is the volume. So I can then write, instead of dV, d A times h divided by dt equal to 10 minus 2h. Okay, I just replace the volume, which is this thing here, with area of the base, which is a circle, times the head or the height. So now I can, and this area, the area of the tank, the base will not change. I mean, even the height is changing, but the area is not changing. So I can take it outside the differential. So I can write the following then: A dH by dt is equal 10 minus 2h. Okay. And now it is an easy problem. You can just solve it by separation of variables. So I can do the following from here. Then I can say what I can say 1 over A dt, I believe, because I will take this dt out there, and then equal to dh over, sorry for this, dh. Let me erase it, it's not clear. So it is equal to dH divided by 10 minus 2h. And the next step is, as usual, to integrate from 0 to t, I believe. And this one, the tank was empty, so I will start from 0. And since I need a relation with h, so from 0 to h. And so on the left hand side, on this side, as you can see, it is just t over a. Okay, and this is equal to what? Now I want to compare this with this equation here that I showed you at the beginning. So your h is the same as your x, and minus 2 is the same as a, and 10 is the same as b. So this is equal to what then? T over a is equal to minus 1 over 2, because a is the same as minus 2, ln what? 10 minus 2h. Okay. And this is what? This is integrated from 0 to h. So we said that let me just write this equation in: t over a is equal to minus 1/2 ln 10 minus 2h, and this is from 0 to h. Okay. Now we want to just to do the usual stuff here, the integration. So I can say, so from here I can just take this thing to the other side. So it will be minus 2 over a times t equals what? Equals ln. And now I want to substitute first as h and then as 0 for the integral here. So this is equal to what? Ln 10 minus 2h. Okay, and this is, and then I will substitute for 0 here. So divided by 10. Okay, and now I can take e for both sides here, e to the left and e to the right. So I will have e to the minus 2 over a times t equals, and if you take the exponential here, so we'll get 10 minus 2h over 10. Okay, and my objective is to solve for h, so I have just to rearrange here. So from here then I can say that 10 minus 2h is equal to 10 e to minus 2 over a times t. And then I can take this, just rearrange it to have h on one side. So then I can write 2h is equal to 10 minus 10 e to the minus 2 over a from t. I can cancel 2 with 10 with 10. This is 5, this is 5, and then I can take 5 as a common factor. You can do this. So from here I can say h is equal to 5, open bracket, 1 minus e to the power minus 2 over a times t. Okay, so this is my final equation. H is a function of t. Does it seem correct? I believe yes. We can check with the initial condition. Whenever t is equal to 0, this whole term, if this is equal to 0, this will be 1. 1 minus 1 is 0. 0 times 5 is 0, and h is equal to 0, which confirms our initial condition. So this is the answer here. This is the answer. So let me just go to the next slide, I think. And you might wonder, why didn't I substitute the value of a? You can substitute the value of a. You know that a is equal to pi d squared over 4, and you have it as 10 feet. So you can substitute it. This is just a constant. Now, I believe this is the solution that we got it, hopefully. And the only difference is a, which is calculated here. And now suppose, as usual, suppose I asked you what is the maximum level that will be reached in the tank? What is the minimum level in the tank? What is the steady, let us say, the steady height of the tank? What is the height at which steady state will be reached? And as usual, I will keep those questions for you to think about and tell me how to tackle them.